This is the second part of the 20th lesson in heat transfer. In the 20th lesson, we have been discussing internal flow convection heat transfer. In the first part of the lesson, we looked at an example of a system that involves internal flow convection heat transfer. That system is the parabolic trough solar concentrating collector. In the second part of the lesson, we will think about what is similar and what is different between internal and external flow convection heat transfer. By the end of this lesson, you should be able to list the most important differences between internal and external flow. You should also be able to list similarities between internal and external flow. And finally, you should be able to explain what it means for an internal flow to be fully developed. Fully developed flow is a flow condition unique to internal flows. External flows can never be fully developed. On with the lesson.
Okay, so to start with, I just want you to try to make a list of things that you think are different between internal flow heat transfer and external flow heat transfer. All right, so there's no right or wrong answer. Just spend a minute and make a list. What's different, right? Why do we treat these subjects differently? Okay. What's different between the two? Go for it.
Now, what I would like you to do is pause the video and write down an answer to the question.
Okay, so Brandon and Zeke, just what was one thing you were thinking about? No right or wrong answer. Okay, good. So I'll try to capture. So I think by limited volume, I know what you're saying. Essentially what you're saying is the flow is confined, and thus there is not an infinite, so to speak, right, energy reservoir. So you can't, like in an external flow, thinking about air, like, air flowing over the tubes of the concentrator, for example, like there's so much mass there that essentially it's like an infinite, in thermodynamics, right, you talked about this constant temperature energy reservoir. That's what it is. I don't see one in an internal flow. Exactly what you're thinking, right? And then something related to, I would say that maybe a similarity is that there's a similarity that so this is a difference. We can think in terms of similarities and differences. It's similar in that we still have no slip, right, at the surfaces. So we're still going to have the effect of viscosity, right? But the question, so that's something to keep in mind. Someone on Zoom, do you want to either chat or unmute yourself and tell us something that you were thinking about? The boundaries. Okay, so the boundaries would be related to this idea that Brandon had, that there's a no slip at the surfaces still, and there's something about this boundary condition. It looks maybe a little different. Okay, good. So I kind of, your ideas are probably all good, all right? But I would say that I would boil down in the differences into two. So this is, you know, my two differences are, of course, are the result of lots of time spent about this, and you're just getting started thinking about it. So that's okay if you didn't have these in your list, all right? But the one is related to this idea of no slip that Brandon and Zeke talked about and what that means for the internal flow. And what's kind of different is that because the fluid is confined, the boundary layer development is constrained, right? So we can think about fluid entering in a pipe, say, over here at the left, and it goes in and it's flowing down the pipe. And we know that the thermal boundary layer is really, really important, and that there will be a thermal boundary layer if the surface of the pipe, for example, is different than the temperature of the fluid, right? So if Ts is not equal to T infinity, we anticipate that the fluid is going to heat up. We anticipate that that's going to happen from the walls in. So there's going to be a thermal boundary layer that develops and grows, but of course, eventually, the boundary layer is gonna meet itself in the center someplace, right? So the boundary layer growth is constrained, and that doesn't happen in an external flow. There is no constraint on the thickness of the thermal boundary layer in an external flow. It can be as big as it wants to be. Okay, so this is an important difference that we'll have to deal with, right? Really important difference that we have to deal with. And it's going to lead to this notion that we have what's called fully developed flow and developing flow. So it's fully developed once the boundary layers meet, and it's developing when the boundary layers are still growing towards each other. Okay. The other issue that we have is that we're going to need a new reference temperature for Newton's law of cooling. Like we've been writing that the flux is equal to H times Ts minus T infinity. But I guess there is a T infinity, but it, like a value of the fluid entering the pipe. But locally, right? If we think about what's happening right here or right here, what's T infinity? What's the temperature of the fluid far away, where the fluid hasn't been impacted by the heat transfer at the surface? Like it doesn't really, there isn't one, and there isn't one, right? Like there is really no T infinity here. There's an entrance temperature, like we should really be thinking about this as a T at x equals 0. It's the temperature of the fluid going in. But most of the time, when we have fluid flowing through a tube, like in the solar concentrator, the whole goal is to heat it up, right? Like we're actually trying to make it warmer or cooler if we were trying to cool it. And so this isn't going to work anymore. This idea of a T infinity is no good. So we need a new reference temperature. We need something that we can write, is H times, Ts minus, what is this going to be? Like, what temperature is the right temperature to write and use in Newton's law of cooling? Right? So we'll have to address that as well. And like the spoiler is that we'll use something called the mass average temperature, or the mixing cup temperature, or the mean temperature. It goes by lots of different names. And if you're in heat power lab, you might have already you've seen this, because you would have had to have used it for the heat exchanger experiment, for sure. Okay, so before we get into unpacking those nuances associated with the convection heat transfer, just like we did with external flow, right? The fluid mechanics is kind of the starting place. So the fluid mechanics is happening, and we need to think about what does that mean for the convection heat transfer in the end, right? So the fluid mechanics is the base, sort of, and then the convection heat transfer is an extension off of that, right? Because convection heat transfer is still conduction plus advection. So the fluid mechanics is the advection part. So if you recall from 373, right, we also have a confined hydrodynamic boundary layer growth. So if you have fluid that enters a tube at some uniform velocity, no slip at the walls slows it down, like we still have no slip. And so we end up with a region in which the velocity changes from 0 up to its, what we call the core velocity. And what's different here in the internal flow is before, with the boundary layer unconstrained, right, we just had some free stream velocity. It's like the velocity of the fluid that was unaffected by the presence of the plate. But the fluid, even in this inviscid core, is going to feel the impact of the slowdown at the walls. because conservation of mass says that whatever the mass flow is through this tube has to be equal, or it has to be constant. We can't be adding or subtracting fluid. So if the fluid at the walls is slowed down, the fluid in the core has to speed up in order to conserve mass, right? Like if we slow fluid down at the walls, we're decreasing the mass flow rate at the walls. The mass flow rate in the core has got to increase in order to conserve mass. So what the boundary layer does in the developing region of the internal flow, it's like a tube of toothpaste, and it's squeezing the fluid down in the middle. It's like you're constricting it almost like the end of a hose, and you're forcing the fluid in the center to speed up. So we have deceleration near the wall and acceleration in the core. So we're actually speeding the fluid up in the core, and eventually this process stops, and the deceleration and the acceleration stops, and we end up with what we call fully developed flow, and we have a velocity profile. And do you remember what well, we'll ask you that in a second. So the other thing that perhaps you could think of as a difference is the Reynolds number that we're going to calculate. We have a reference length now as the tube diameter. It's a really handy reference to use. And so we're going to calculate Reynolds numbers based off of that reference. And then often it's going to be more convenient. We're going to know something about the mass flow rate of the fluid. And so we can take advantage of the fact that m dot is equal to rho times the average velocity times area, right? That's the thing that you've seen from thermodynamics. And if you solve that for u, right, so u is equal to m dot over rho a, and you put that in here, you get the equation on the right, which is another way of calculating the Reynolds number for an internal flow. You can base it off of the mass flow rate, because the mass flow rate does tell you something about the average velocity. So this is, and we'll have to talk about this too, this is an average velocity, because there is no one velocity, see? There's a distribution of velocities, and there's no free stream velocity to use. So we have some other way. We can have laminar and turbulent flow, and now we remember that 2300 number for turbulent flow. If you have a Reynolds number bigger than 2300, it's pretty much guaranteed to be turbulent. If it's below 2000, it's guaranteed to be laminar. If you're somewhere in the middle, it's tricky. It could be laminar, it could be turbulent, it could go back and forth between laminar and turbulent and be sporadic. It's a weird region. Okay, so that mass average velocity, I was using u before, and you'll see this also as u, a capital U, and sometimes you'll see a u sub m. It is this, the velocity that you calculate when you take the mass flow rate and you divide by density times area. Or you can take the volumetric flow rate, right, because m dot is equal to rho times the volumetric flow rate, and you divide by area, right? So you put that in and the densities cancel. And do you remember that for fully from 373, in a laminar flow, the velocity profile is parabolic in shape, goes to r squared. And you don't have to try to write all this stuff down. It's on the slides, right? Like go and get it later from the slides if you want it, or go and look at your fluid mechanics notes. And if you look at this equation right here, I like this one the best. When r is equal to 0, okay, when r is equal to 0, this term becomes the whole bracketed term becomes 1. And so when r is equal to 0, the velocity at the center line is 2 times the average velocity in a fully developed laminar flow. The velocity at the center line is 2 times the average velocity. So the average velocity is like, you know, if you wanted to think of the equivalent uniform velocity, it's like half of that parabolic velocity profile. So it's all ringing some bells. This should hopefully be reviewed mostly. Okay, and then this is the true fluid mechanics part. We needed to write friction, right? Friction is what we left out of the story with Bernoulli's equation. And so we had to put that back in. And that's captured with something called ultimately the Darcy friction factor. We just called it the friction factor. It goes, Darcy is an extra, is to kind of pay homage to the engineer that first thought about it. And you can get that friction factor from a thing called the Moody chart. Remember that? So there's a Moody chart in your textbook as well, okay, which is the same Moody chart from the fluid mechanics book. Or you can use the Colebrook equation, which hopefully you might still have the MATLAB function from fluid mechanics if you had fluid mechanics with me. And the way that we calculate the pressure drop, which is what pushes the fluid down the pipe, is with that friction factor. It's scaled on the kinetic energy of the flow in the pipe. 1/2 rho mass average velocity squared times the friction factor over the diameter gives you the pressure drop per unit length. That also should be kind of review. So just know we've got this pressure drop that is there because of friction, right? The pressure drops to overcome the friction at the walls. And the friction at the walls is there because there's a shear stress that develops at the interface there. Fully developed flow. At what point do the boundary layers meet? Right. So if you're in a laminar flow, it's based off of the Reynolds number. You take 0.05 times the Reynolds number times the tube diameter, right, or 2 times the tube radius. And that's where you have fully developed conditions. If it's turbulent, it's really complicated, but generally it becomes fully developed by 10 diameters down from the entrance. Okay, so that's all the fluid mechanics review. Any questions on the fluid mechanics side? Okay, so then starting to turn then to what this means for heat transfer. First, we'll think about if we anticipate that there's a hydrodynamic boundary layer, right, that grows in the developing region of an internal flow, then there should also be a thermal boundary layer that grows. How do you think we could estimate, right, if we know that the hydrodynamic boundary layer becomes fully developed at this location, and that this location somehow relates, right, to the thickness of the hydrodynamic boundary layer and how quickly it grows? Do you have a guess as to how we calculate the fully developed length for the thermal problem? Like, how would we translate this to the thermal problem? Knowing what you know about, say, our discussion of external flow and what tells us something about the relative thicknesses of the hydrodynamic boundary layer thickness and the thermal boundary layer thickness. What do you think? What property? Chase?
The critical Reynolds number.
Okay, the critical Reynolds number would still apply, and we would also have the notion that, you know, the boundary layer could start laminar here, and it could also transition and become turbulent, even if we say had nice laminar smooth flow on the inside, right? We could end up with some weird things happening in here, and that would be dictated based off of that critical Reynolds number. But that's not what I was thinking of. I'm thinking of a fluid property. Okay. Daniel?
Prandtl number.
The Prandtl number. The Prandtl number, right, remember, is represents a ratio of the hydrodynamic and thermal boundary layer thicknesses. So in a laminar flow where the thickening of the boundary layer is driven by diffusion, right, the Prandtl number links those two things together. And so when you go and look at the thermally fully developed length, all we have to do is multiply by the Prandtl number. It's the exact same equation, basically, for the hydrodynamic developing length. You just multiply that by the Prandtl number. So that means for gases, right? If we have gas flow through tubes, gases have a Prandtl number around 0.7, close to 1, basically, right? And so the hydrodynamic developing length and the thermal developing length are going to be very similar. But for oil, right, oil has a really large Prandtl number, could be as high as 500, right? So you're going to hydrodynamically develop very quickly and end up with a uniform, for a laminar flow, a parabolic velocity profile, but the thermal boundary layer will still be growing, right? Because the Prandtl number is big, and so the developing length thermally could be a lot longer than for the hydrodynamic one. And then you have liquid metals where you could very quickly develop your thermal boundary layer and you have your thermal boundary layer meet, but the hydrodynamic boundary layer is still growing, right? So you still have a relatively flat velocity profile and accelerating fluid, even though the thermal boundary layer is met already. The Prandtl number is the link between the two. And that's why it shows up here. Now, it's crazy, but for turbulent flow, because turbulence transport's dominated by the mixing of the turbulent eddies, the Prandtl number doesn't have as much of an influence over the relative rates of the growth of the boundary layers, because the Prandtl number is really linked to a diffusive transport, not this turbulent mixing. And so for truly turbulent flow that starts turbulent and goes in, it's really difficult to predict, but kind of the rule of thumb is about 10 tube diameters down, you're fully developed. That's true for both hydrodynamic and the in a thermal sense. Okay, questions on that? So that's kind of still thinking about differences between internal and external flow. So one of the differences is we have these two regions in an internal flow, a developing region and a fully developed region. There is no such thing as a fully developed region in an external flow. It doesn't exist, right? So the developing region in an internal flow has a lot of similarities to the external flow. The fully developed region bears no similarity to external flow. It's a completely different animal. Right, so we'll have to spend actually most of our time thinking about what's happening in the fully developed region because we don't have anything available to help us with that yet.